Hi, my name is Jim, and today I'd like to show you the project that I've been working on with the Analog Devices ADF5355 microwave synthesizer. What got me going on this project was my desire to create microwave frequencies at home for cheap. I didn't want to spend thousands of dollars on a piece of test equipment, so I started doing research to find out my options as to how I could create microwave frequencies as cheaply as possible. The first thing that I came across in my research was the ADF4351 chip, which is a similar complete solution microwave synthesizer chip from Analog Devices, and it does have quite a bit more support already out there. But the problem is it only extends into the 4 gigahertz range, and really what I was targeting was the amateur frequency allocation in the 5 and 3 centimeter ranges. I think it would be very interesting to start experimenting in these amateur frequency bands. Now, when you go to the Analog Devices website, the next model up from the 4351 is, of course, the 5355. And they do, in fact, offer the 13 gigahertz chip, the 5355, in a complete eval kit. The problem is, the eval kit is $500. So from there, I decided on the eBay board that you see here on the left, which is available for $90 and features basically a complete evaluation kit. It's a clone of Analog Devices evaluation board. You can see it's scattered with passive components for the loop filter, 2 voltage regulators for the power rails, a 25 megahertz clock, a couple of optional reference inputs, and a center positive DC jack. What this board does not include, however, is any means to communicate with it. If we look at the Analog Devices board, it actually comes with a microcontroller that has some proprietary software on it that's able to interface with the computer. So by going with this eBay board, basically all of that has to be taken care of myself. So with that being said, the question now becomes, how do you communicate to the ADF5355? The answer, of course, is in the datasheet. It uses an SPI interface with a latch enable, a data line, and a clock line. The latch engages, the clock starts counting, and the data gets sent to the device. So now I'll show you how I achieved that communication. It starts with a graphical user interface written in C#, where all of the device parameters are set and then sent to an Arduino over a serial bus. From there, the Arduino converts the register information to an SPI protocol to be read by the synthesizer. An important part in the development process was the ability to decode the SPI data that was being sent to the synthesizer. To do that, I just used a logic analyzer with the PulseView open source software and wrote a small Python script to decode the data into meaningful parameters that were being sent to the device. A distinguishing feature that I included in this project is the ability to sweep the frequency arbitrarily with an external input. This feature is not available on the Analog Devices evaluation board, but including it here really adds similar functionality to actual lab bench frequency synthesizers.
The window on the right is the official Analog Devices evaluation board control software. Upon selecting the 5355, we're presented with a full control panel of all of the device parameters and register contents. Without the official evaluation board, we can't actually use this software to upload these parameters to the device. But one feature that the software does have is the ability to dump all of these register contents into a text file. So from there, we can then parse that text file and upload it to the Arduino, and from there, create the SPI commands.
Taking a look at the test setup, we have a 200 megahertz Tektronix analog oscilloscope. The frequency synthesizer here is terminated into a 50 ohm load and T-tapped into channel 2 of the oscilloscope. On top is a signal generator that is connected to the analog input of the Arduino and is being probed by channel 2. Tapped into the SPI line is a logic analyzer. To initialize the synthesizer, first you have to set the desired register parameters. For example, we're using a 25 megahertz clock, reference frequency clock, and we can use the reference divide by 2. This will increase our frequency resolution at the cost of some phase noise performance. And let's set the output divider to the full divide by 64. So now these register contents will produce a VCO output of 6.6 gigahertz divided by 64, so we'll see on the oscilloscope screen 103 megahertz. Now with the synthesizer parameters set, we can go File, Dump Register Contents, Save. Now a text file containing all of these register contents has been created, and we can go to the C# Windows form that I wrote in order to parse this text file and send it to the Arduino. So we'll connect to the Arduino, hit Update Registers, and run the initialization sequence.
And now you can see the waveform being displayed on the oscilloscope.
The voltage that you see sweeping up and down on the oscilloscope is the external input generated by the external frequency synthesizer. Now this waveform is a triangle wave going from 0 to 5 volts, and this will be controlling the frequency output of the ADF synthesizer. To control the frequency sweep, we have to set the frequency output to the maximum peak frequency value. Dump this register contents, upload the registers to the Arduino, and run the frequency update. Next, we need to determine what is the minimum integer value that we want to sweep down to. Well, the minimum output is 3.4 gigahertz, which results in an RF out of 53 megahertz, and that occurs at an integer value of 272. So we'll set the integer value to 272, set the sweep duration, and start the sweep. Now on the oscilloscope you can see the frequency varying proportional to the input voltage. The way the C# form works is that each button sends a predefined string over the serial port. This predefined string value is expected on the Arduino side, and based on which string it receives, called the command string, based on which string it receives, it then performs a certain action. For example, the frequency hopping, in order to send the hop period value, it parses the text value that's in this form, sends the command followed by the actual value, which is then received by the Arduino and converted into an integer value for the period. To make sure everything's working properly, let's run a fast hop between two frequencies and capture the SPI data with the logic analyzer. So to do so, let's just set two random frequencies. We'll dump the first one as register values, and we'll dump the second one as the hop register values. Now we can connect to the Arduino, update the initial registers, update the hop registers. Set a pretty fast hopping period of 10 milliseconds, a couple hundred hop cycles, and now let's capture this data in the PulseView software. Run and start hop. Now that all of the data is populated, let's see what happened from frequency update to frequency update. Well, here's the serial data, but it's almost impossible to understand. So now here's where the Python decoder that I wrote comes into play. You select the SPI bus, stack decoder, and select the 5355 stack decoder. After a second, it populates all of these register values with the actual data and parameter being sent to the synthesizer. For example, here's register 4, and the phase detector polarity is a 1, which is positive. The current setting is at 94 milliamps, which corresponds to a 0010, and the 10-bit R counter is at 0001. Next, I'll show you a closer look at how exactly this 5355 register decoder is working. Taking a look at the Python script that I wrote to decode the serial data, you can see it was really quite simple. It was just a matter of taking an existing decoder template and then filling in the register data based on the synthesizer datasheet. So, for example, looking now at register 4, you can see its register 4 contains all of these different parameters that control the synthesizer chip. The counter reset, the charge pump 3 state, power down, the phase detector polarity. So, for example, the phase detector polarity is at bit 7 and is a 1 bit in width. So there's two options, 0 or 1, which pertains to a negative or positive phase detector polarity. So, looking back at the code, for register 4, the phase detector polarity is again at an offset of 7, is 1 bit in width, and then returns either negative or positive. And basically the whole script just goes through each individual register and bit location within that register and assigns the correct value. So it just makes it so much easier to figure out what you're actually doing rather than looking at zeros and ones. You can say, okay, I'm in register 4 right now, and I just set the 10-bit counter to 1023. Let's check with the datasheet to make sure that the frequency update sequence is executing as expected. According to the datasheet, the first thing that needs to happen for the frequency update sequence is I write to register 10, and then I write to register 4. Looking at the serial data, sure enough, the first thing that happens is I write to register 10, then register 4. But it says on register 4 that the DB4 bit must equal 1. The counter reset must be enabled. And sure enough, looking at the first write to register 4, bit 0, 1, 2, 3, 4 is set to 1, and the decoder tells us that the counter reset is in fact enabled. And if you remember, I set the frequency hop time delay from each frequency update to 10 milliseconds. So sure enough, each one of these frequency update packets are 10 milliseconds apart. Looking now at the phase noise plot of the synthesizer, at first glance, it looks really, really good. Better than minus 90 dB, especially at further offsets from the carrier. So then the question is, when you're looking at the signal in the time domain, why does it look so distorted? Well, the answer to that is the harmonic content. Although the phase noise performance of the synthesizer is very, very good, the harmonic performance, not so much. Using the divided VCO output, the second harmonic is only 22 dB down. The third harmonic with the divided output is only 12 dB down. So if you were to look at this signal in the frequency domain, it would really just look like a comb of frequencies across all of these different harmonics, which really makes sense when you think about the way that this chip operates, right? It's a single VCO that is then divided many, many times down in order to get the frequency that it's operating at. The VCO itself is 0.4 gig to 6.8 gig, but we're dividing and dividing and dividing, and just the nature of that action is what's causing all of these harmonic spikes, and that's why you're getting this distortion. So the takeaway from this then is that when you go to use this synthesizer in your application, you're almost certainly going to need to filter it before it enters the next stage. For example, if you were to use it as the local oscillator of a super heterodyne receiver, you would probably have to put a filter stage right in front of the oscillator before it goes into the down-converting mixer, just to eliminate a bunch of spectral garbage that would otherwise be produced at the output of the mixer. This concludes the video on the microwave synthesizer project. Unfortunately, we didn't get to see any actual microwaves because we were limited by a 200 megahertz scope, but I think we were able to prove that we now have full control of the evaluation board, and we also added this additional functionality of being able to sweep the waveform with an external source, and I think this will prove very useful when interfacing the signal to your device under test and future experiments. Thank you.